In the rapid development of artificial intelligence today, large reasoning models have demonstrated astonishing problem-solving capabilities. However, researchers have found that these models may fall into the dilemma of overthinking in practical applications. They overly rely on internal reasoning while neglecting external feedback, a phenomenon that significantly affects the model's practical performance. Today, we will share the latest research findings from institutions such as the University of California, Berkeley, and ETH Zurich. This study is the first to systematically reveal a fundamental challenge faced by large reasoning models in practical applications: the reasoning action dilemma. This dilemma can be likened to programming. Imagine a programmer solving a bug, who has two choices: directly attempt to fix and run the program to see the effect, direct interaction with the environment, or carefully analyze the code logic and simulate various possibilities in the mind, internal reasoning. The ideal working method should be a balance of both. First, do some analysis and reasoning, then put it into practice to verify the ideas, and then proceed to the next step of thinking based on the practical results. The same applies to AI models, which need to find an appropriate balance between thinking and acting, both planning decisions through internal reasoning and interacting with the environment in a timely manner to obtain feedback, validate, and adjust their judgments. Specifically, the research team analyzed 3,908 software engineering task trajectories and identified three problem patterns caused by over-reliance on internal reasoning. The first type is analysis paralysis. The model becomes overly focused on creating detailed plans, getting stuck in an endless internal reasoning loop, and delaying taking actual action. That it's like a programmer facing a bug, continuously analyzing possible causes and devising complex solutions, but never attempting any specific repair steps. The second type is rogue actions. In this case, the model presets the results of multiple consecutive steps in its internal reasoning, leading to the execution of multiple operations simultaneously without waiting for environmental feedback. This is like an engineer when the system fails, executing multiple repair commands based on their own speculation, instead of waiting for the actual effect of each operation. The third type is premature disengagement based on reasoning. In this case, the model internally conducts a lot of reasoning and prejudgment, believing that it has verified all possible outcomes in its mind, thus making conclusions prematurely. Either it concludes that the problem is solved based on reasoning and no longer verifies, or it reasons that all hypothetical paths cannot solve the problem and gives up trying. This is equivalent to an engineer completely relying on experience and reasoning to conclude that the problem is unsolvable, without actually trying various possible solutions. Research has found a significant negative correlation between overthinking and task success rates. Models with reasoning capabilities are more prone to overthinking than typical language models, LLMs, with their overthinking scores being nearly 3 times higher on average. This suggests that the stronger a model's reasoning ability, the more likely it is to fall into the trap of overthinking. Faced with the issue of overthinking, researchers have discovered some effective coping strategies. First, adjust the model's reasoning effort. When reducing the reasoning effort, although the model's success rate drops from 29.1% to 21%, this adjustment brings significant efficiency improvements. The computational cost is reduced by 3.5 times. This is like controlling the depth of analysis when solving problems, avoiding getting stuck in overthinking. The researchers subsequently discovered a more interesting method. They attempted to generate two solutions with low reasoning effort, and then selected the one with a lower overthinking score. This method achieved surprisingly good results. The success rate could reach 27.3%, almost approaching the level of high reasoning effort, while the computational cost was reduced by 43%. This strategy is like letting the model try multiple solutions with a relaxed mindset and then choosing the most natural one. Looking ahead, the research team proposed two possible directions for improvement. The first direction is to enhance the model's native function calling capability. This is like teaching the model to use tools more effectively, rather than relying solely on its own reasoning for everything. Preliminary experimental results are encouraging. Models with function calling capabilities not only perform better, but also exhibit less overthinking. This suggests that enabling models to better utilize external tools could be an important approach to addressing the issue of overthinking. The second direction is the selective application of reinforcement learning. This method can help the model gradually learn when to think deeply and when to act promptly. Research in this direction is still ongoing and may bring more breakthroughs in the future. Finally, let's take a look at the rigor of this study in terms of data validation. The research team employed two important statistical methods to ensure the reliability of the conclusions. First is the Wilson score method, used to calculate confidence intervals. This method can tell us how reliable the experimental results are. Simply put, it's like drawing a trust range for the experimental results, letting us know within which interval the true situation is most likely to fall. Next is regression analysis, used to reveal the specific relationship between overthinking and task success rate. The study found an interesting phenomenon. For reasoning models such as O1, QWQ, etc., every time the overthinking score increases by 1 point, the task success rate decreases by 7.894 percentage points. It's as if the model moves further away from the correct answer with each additional thought. For non-reasoning models such as GPT, 4o, Claude, etc., every time the overthinking score increases by 1 point, the task success rate drops significantly by 15.938 percentage points. This indicates that once ordinary models fall into overthinking, their performance declines more rapidly. This discovery is particularly interesting. Although reasoning models are more prone to overthinking, they seem to better withstand the negative effects of overthinking. That it's like how professional chess players, even if they think too much, their performance doesn't drop too severely, while amateur players are more likely to make mistakes once they overthink. This research is of great significance for improving the practical application effectiveness of AI systems. That IT reminds us that while pursuing the reasoning capabilities of models, we must also pay attention to maintaining a balance in their interaction with the environment. Just as humans need to pause and verify when solving problems, AI systems also need this balancing capability. The research team has open-sourced their evaluation framework and dataset, which will help more researchers delve deeper into this field. As research progresses, we may be able to develop more efficient and practical AI systems.